all the way through and never find that red square. So it's going to be better in memory. It's going to be a little bit faster maybe, but there's got to be better ways to do this, especially when we have some obstacles. We can get there eventually, but breadth first search keeps on doing sort of a flood fill, expand as much as possible around where I am. So what we could do is start to incorporate the idea of a heuristic. Heuristic is a way to think of a rule of thumb. How could I estimate what I should be doing for a square? These squares are not equal. Some squares should be better to look at than others, and why? Breadth first search says it's a square. It's not the square I want. Where else can I go? But we can add a heuristic to say, why would I want to search one square over another one?
Possibilities that it has? The number of neighbors, basically?
The number of neighbors might be a factor. There's another bigger one. Why would I want to search this square instead of that square?
That direction is more towards the rest of the search space.
This one is closer, not just the rest of the search space, closer to the red one. Breadth first search doesn't even care. It just keeps on looking, even though these are irrelevant and they're getting worse and worse and worse. It just keeps on expanding them. So we could do something called best first search, which says instead of queuing them up, instead of stacking them up in our search, we're going to order them based on this heuristic, based on this idea of how far away you are theoretically just looking at the node itself. I don't know about the obstacles and exactly what's going on, but this one, this one is pretty close, so I should look at that one next. Okay, so best first search follows a path like this. We can look at it, and it says, I want to go towards that red square. It runs up against our boundary and says, I can't. So keep on looking around it until I get a way around it. Best first search takes the places we could go and reshuffles them. It's a priority queue, if you looked at priority queues before. Now we don't just have a queue of things, but pieces get bubbled up. Maybe we use a heap to implement it, or maybe something else lets us put those things in an order. But best first search also has some problems. Is that the most optimal way to get there? It is. Let's try to do this again over here. Is that the most optimal way to get there? No. Why not?
So it doesn't have to go so far.
Yes. We were queuing them up with the priority of what's going on. We explored this whole space. We came back out, found better ways. But we never said that jumping in was a failure. It was not a good idea for us to be searching. Okay, so the way we can fix this is with an algorithm called A star. Are there any questions about best first and what it's doing? A star takes the approach of using best first search and combining it with knowledge of where we've been so far. We've been searching with best first search, just looking at an individual node and saying, how far are you from where I want to go? But we also need to consider the total path along the way. We want to be searching among paths and not among individual nodes. So A star lets us combine those different things and says our real estimate of what's going on is based on the total sum of where I have been, the path of the cost of the path so far, plus what's happening, I think, in the future. We don't want to just look at the past. We don't want to just look at the future. They all have to come together for us. And it's an estimate, but it is guaranteed to find us that best path again. A star pushed us back further because this one down here, that breadth first search or best first search was finding, had a worse initial cost. So by putting those pieces together, A star found the optimal path, the same one that breadth first search would find. Takes forever, but it will eventually find a very similar path. Should cost about the same. And it is much faster to do A star. Okay, so nice visual website out there. Here's another one. This is the power of A star. Imagine you're in a game, and this is your red star is where you are. You want to get there. You can dynamically figure out this path depending on where you are by using some sort of A star search in the background. And you can move this piece around. Underneath this idea is an A star search. Figuring out optimally where I want to go, efficiently, not wasting all that space. Here's another example of breadth first, expanding those nodes. That's that idea behind breadth first search. Just keeps on going, but if we can order these nodes in a different way, based on that heuristic and what we've done so far, then we can better search this space. Queue, make it a priority queue. And just so you have that visualization, when you do find out where you want to go, there are these arrows, these links back to your original spot. Anywhere out here can find its way back to you just by following those arrows. And the path is created recursively at the end of this whole piece. Does that make sense? Okay. You can also be incorporating a cost of each node itself. You can say some of these nodes require me to wander through the desert or to climb a mountain. And it's not just an obstacle that I can't go up and down, but it's something that will make me go slower through it. You can incorporate that into your squares, your nodes of what you're searching. And if you just do it based on the number of steps, you're going to just run right through the mountain. But if you care about that the green ones cost you more to step on, then that can be incorporated into what you're doing as you move through. And then the way you search is not just a flood fill, but it starts to focus in on avoiding very expensive places in the space, etc. Yes, and here's that problem we saw with a greedy search. It digs itself into a hole, but A star says this is that best first. This was our breadth first. We put them together to search those whole paths all at once. So, wonderful animations out there on the web that I did not recreate. I don't take credit for these. But hopefully they're really explaining this concept visually for you of what's going on between your spot and a target that you want to get to. You have to figure out how to get there. And it's a search problem. Search problems are everywhere. in computer science. I need to figure out the optimal way to do something. This is one of those examples. You might have seen it in robotics, artificial intelligence, or other places out there have this idea of a search that we need to do efficiently. This is one very, very common way to do it. Okay, any questions about search A-star? Had you heard of A-star before? Maybe one or two of you from artificial intelligence or robotics or something. Okay, hopefully this puts it into context of what we're going to do in this class with pathfinding, navigation, looking for the optimal way to get from one spot to another. Okay, so let's jump into Unity and see what it can do for us. And I think I want you to download Unity 5. I've looked at it on paper. I haven't downloaded it myself, but it includes all the features that Unity 4 said you used to pay for. So that's wonderful. One of them is this navigation idea. There is a navigation tab that'll show up here next to the inspector. If you go up here to the window and say, I want to look at navigation, the navigation tab will show up. And you can say, my world needs to care about navigation. I need to start thinking in terms of what's possible for agents to move around and how they move. And we saw this concept before of baking. What did I talk about baking before? Does anybody remember?
Game remembers that you never want to change that.
Yes, we were baking and thinking about baking lights. You know that this light is always going to be shining in this place on the world. So instead of dynamically every time rendering pixels and saying, aha, this light is shining, I need to make that brighter every single time, you can bake your lights in a game and really speed up your processing. So the same baking idea can happen inside navigation. I have my world. I need to figure out what are the places I could go, and you're going to bake something called a nav mesh, a mesh for navigation. Now meshes are those triangular pieces that let us compose our objects in the world. This is going to be a triangular thing that lets us navigate through it. What we were seeing in those examples were a bunch of squares. Well, it's better to use polygons. It's better to use triangles in our example. So that's what a mesh is, a bunch of triangles. A mesh being used for navigation is called the nav mesh. Okay, so let's make a simple world here. Let's make a plane. There we go. And here's what we can do. I click on that, and in the navigation screen, it says care about it. If you do want to care about it, you want to say navigation static. This thing will not be moving, and I'm going to make it part of the default layer. There's options of what happens when we bake things. It says you're going to put a radius on it. There's a certain height. There's a slope that can happen, step height, other different pieces going on. Really, the radius is what I want to look at right now. And I want to bake. Let's save my scene here. It puts this blue layer on top that you only see when you have the navigation tab selected. There's this invisible blue square on top of where you are. This is the navigation mesh. Doesn't look very complicated right now. It's just a big square because everything is open. There's no obstacles. There's nothing else in this world, just a place to navigate. But the radius that we picked said, I really don't want to go off the edges. So I could pick a radius of 1. And it says stay away from those edges even further. The radius is how far away from obstacles and things we want to be. So